SwayamPrabha. Digital India. Educated India.
Hello everyone. So, we will continue with water filtration by nanomaterials. So, what we are discussing in last session, we are continuing with the nano adsorbents. So, here another nano adsorbent is zeolites. So, the advantage here is that it is a very porous structure in which nanoparticles such as silver ion can be embedded. So, in a zeolite it is a porous structure that which embeds the nanoparticles, like silver nanoparticles can be embedded, and the collected release of nanosilver. So, it is a controlled release, it is there. The nanoparticles, silver nanoparticles, as they are embedded. So, whatever waters are collected, water is collected, there will be very minimum acceptable limit of the silver nanoparticles, nano silver. So, that the collected water will be the almost 0, there is no silver nanoparticles will be there, or we can, if we want, we can control the release of nanoparticles. Because here we want to kill the bacteria, okay, bactericidal. So, what it is required, if it is in the fiber form, we have to expose this nano silver particle on the surface, that we have to expose, and so that it can release the nano silver in the controlled fashion, and so that it can react with the bacteria and bacteria can be killed. The application here is it is a disinfection process. So, where in the infection is there in, so in that process we can use this. And another nanomaterial is that the nanometal and nanometal oxides. So, earlier we have discussed that nano adsorbents, now it is a nanometals. So, nanometals, these are a promising alternative of carbon. So, alternative to the activated carbon here. So, nanometals we can use in place of activated carbon, effectively adsorb and remove the heavy metals and radionuclides. So, it can easily remove. So, the examples are basically, so nano silver, nano titanium dioxide. So, these are the material which can be used to remove the heavy metals. So, nano silver exhibits strong and broad spectrum antimicrobial activity basically. So, this nano silver, for any antimicrobial activity we can use nano silver. So, it has least harmful effect, actually up to certain ppm level as per the World Health Organization, So, certain ppm level we can use this and nano silver. So, nano titanium dioxide also it is featuring high chemical stability, low toxicity to the human and very long lifetime, and it is a cheaper in price. So, these two types of material we can use nanometals or nanometal oxides. However, nano titanium dioxide requires UV activation. So, to activate the nano TiO2 titanium dioxide, so UV activation is required. So, the applications are point of use water disinfection. So, that we can use, so anti biofouling. So, that this type of surface we can use. So, decontamination of organic compounds, remote areas we can use where power is not there. So, all these applications we can use this type of nanomaterials. And also among the nanometals we can have magnetic nanoparticles can use. So, magnetic nanoparticles can be injected directly into the contaminated ground. So, ground contamination we can remove, and the loaded particles can be removed simply through the magnetic field. So, it is this magnetic nanoparticle used for separation of water pollutants already been established. So, this technology is established for groundwater remediation and in particular for removal of arsenic. So, in groundwater arsenic if it is there we can use that magnetic nanoparticles Fe3O4 magnetite we can use. The applications, so groundwater remediation we can use. Now, the third variety is that nanofibrous filter media. This is very important. In the latest technology of nanofiber manufacturing. So, that latest manufacturing of nanofiber actually creates the nanopores. So, web, and this web can be actually used in along with other type of substrate, maybe melt blown or maybe spun bonded. So, this fibrous filter media main advantage is that it is highly porous, and due to its high surface area the filtration efficiency will be very high. So, that main challenge was that to fabricate the nanofiber mat. So, we want to produce a nanofiber mat, porous mat, and another thing is the nanofiber manufacturing is that the homogeneity in the diameter and its distribution. So, it has been observed when we produce nanofiber the diameter distribution is wide, the homogeneity is not there. So, that is a mixture. So, that is the main challenge in this nanofiber mat manufacturing development. So, attaining the uniformity. So, uniformity in deposition. So, when we deposit the nanofiber on a substrate, this normally not uniform, the thickness varies. In some places it is different than other. So, thickness and structural like porosity and structural indexes. So, different types of structures, whether this may be on some place compact, some place open structure, porosity may be different, thickness is obviously different. So, overall the areal density of at different places are different. So, uniformity, attaining uniformity is of the wave is very difficult. So, one is that attaining the uniformity in diameter of nanofiber is difficult, and attaining the uniformity in the deposition. So, these are the different challenges which we face, and also we should get one material in a mat which is durable, because it is a very weak, because the nano wave they are very weak. So, durability is the issue. So, nanofibrous filter media. So, we use nano wave, we produce nano wave. So, the major processes for producing nanofiber is that electrospinning. So, there are different process, electrospinning is one major process, then improved modular melt blowing. So, if we change the melt blowing process, if we in melt blowing process the fibers are diameters are much lower than the spun bonded in micron level, but if we can improve, if we can have more stretch, then we can create the nanofiber also in melt blowing. Multi-component fiber spinning, that way also we can produce, like if we produce a fiber with core sheath structure, like it is called island in sea type of structure, then this matrix component we can, if we remove, then we can calculate, we can produce the nanofiber. Multi-component fiber spinning, one component is actually removed, but most versatile process of production of nanofiber is electrospinning, which is widely used in the industry, in the research we widely use. This is being used for producing nanofibrous membrane over wide range of porosity, that we can change the porosity, even different types of polymers we can use, different types of coatings we can use, and we can produce different macroporous delicate fiber structure we can use. So, due to all this versatility, the nano fibers mat we can for producing nanofiber mat. So, electrospinning is the very popular choice. So, let us try to understand very short the electrospinning process. So, this electrospinning process is very useful in producing the fiber within the range of 5 nanometer to 500 nanometer, at that range, and where we can get continuous nanofiber, and we can form a wave which is typically very uniform wave we can produce. So, all the shortcomings of nanofiber production we can overcome by using the electrospinning, and this system is now stabilized and optimized systems are available. So, another advantage is that in electrospinning it is capable to process synthetic material, natural material, metal, ceramics and also composite material. So, through the electrospinning we can produce many we can use many different types of materials, and most of the polymers are dissolved in solvent. So, that is why in polymer we can use forming a viscoelastic polymer solution. So, polymers are dissolved in a solvent to produce a viscoelastic polymer solution. So, polymer will definitely most of the polymer will actually be dissolved in some of the solvents, and then this viscoelastic polymers are used for the nano spinning. We can see here, and the polymer solution which was actually we have discussed this after dissolution in the solvent, this polymer solution is actually injected through the syringe, then fed to the syringe and drive to the electrospinning. So, that it is through the syringe the solution is injected through the spinneret, and then it comes under the high voltage area. The electric field, high volt electric field is applied between the syringe needle and the metallic collection surface. This is the collector, and this high voltage difference will be responsible for generating the nanofiber. So, when the intensity of the applied force, the electric voltage, electric field is increased, okay, and the hemispherical surface of the solution which comes normally through the syringe, this is the hemispherical surface, this type of surface will be developed at the tip, okay, of the capillary. Then it due to this voltage it will start elongating and forms a conical shape which is known as the Taylor cone. So, it will form a conical shape, like this type of shape it will form due to the applied electric field. So, then this total nanofiber will be will generate and it will be collected on the collection surface. So, this electric field when we increase, that actually reaches the critical value where repulsive electric force overcome the surface tension force of the polymer solution, and that when it is overcoming the surface tension, then the polymer will actually start the charge to be ejected and it will start forming the Taylor cone. So, at this critical value a charged jet of the solution is ejected. So, here you can see this is the spinneret and this was the hemisphere, and due to the electric field when it is overcoming the surface tension, then it will start ejecting from the tip of the Taylor cone. This is the tip of the Taylor cone and the electrospun filaments are generated. And during this process the solvents which were there, the solvent will get evaporated in the air. Okay. and the dry polymeric nanofiber, the dry polymeric nanofiber will get deposited on the surface. So, charged polymer fiber is randomly deposited over metallic collector due to the this charge, it is collected there, and molecular weight, viscosity, conductivity, surface tension, all these characteristics of polymer solution are important parameters. If the surface tension is very high, then we need high electrical force, otherwise the electrospinning will not be possible, like viscosity, weight, molecular weight. So, everything this all these things are important. Along with this processing parameters like operating voltage, tip to target distance. So, what is the distance, like here you can see just this is the distance, tip to target, this distance is important. So, this here it is on the vertical orientation, also we can have electrospinning in horizontal orientation. The process will be same. So, tip to target distance, what is the temperature is kept, what is the pressure is applied, and the flow rate, what is at which flow rate it is we are pumping this polymer solution, and all these parameters control the fiber characteristics, quality of fiber. So, the main advantage of electrospun nanofiber in water filtration are due to its high porosity, we need lower pressure, unlike RO membrane where high pressure is required. So, here in nanofiber filtration we its high porosity is there, we can produce large quantity of we process large quantity of water. For water treatment we can use, it is a tailor made, depending on our requirement we can produce this high permeate efficiency because of the high porosity. So, it is as it is a nano fiber is there, we can treat with the different nano material. So, bacteria it can remove, and disadvantage is that pore blocking. So, due to the uneven pore size and it is a that nonwoven fibrous structure, so particle will penetrate inside, unlike the membrane where surface is smooth. So, here surface is not smooth. So, the particle can block the pores. So, it can sometimes it releases the nanofibers during the filtration. So, it releases the nano fibers during the filtration. So, main applications are, so in filter cartridge we use the nanofiber mat, ultrafiltration we can use nanofiber, and pre-filtration water treatment plant we can use, and standalone filter device. So, all this application we can use this nanofibrous filter medium. Along with the electrospun nano material nanofiber, we can use nano composite nanocomposite membranes we can use. So, along with membrane we can use the nano fiber. So, two groups of filtration media comprising of mixed matrix membrane and surface functionalization membrane. So, two types of membranes can be used. So, matrix membranes are used by the nanofiller. They use nanofiller which are added in a matrix material, and in most cases the nanofillers are inorganic and embedded in a polymeric or inorganic oxide matrix. So, this the different types of nanocomposites. These nanofillers are large, they have large specific surface area. So, leading to higher surface to mass ratio. So, it enhance the filtration capacity. So, metal oxide nanoparticles are used. This can help in increasing the mechanical and thermal stability as well as the permeate flux of polymeric membrane. So, with the membrane we can use the nanoparticle, so which enhance the characteristics. So, antimicrobial nanoparticles also used along with the membrane, the nanosilver, carbon nanotube and photocatalytic nanomembranes. Okay. These are mainly used in increasing the resistance to fouling. So, more than one type of nanomaterials we can use to form nanocomposite membranes. Basically, these nanocomposite membranes are used generated by adding superhydrophilic nanoparticle to a polymeric thin film. So, what is done, a polymeric thin film is there, okay, and where the nanoparticles are embedded, and these are superhydrophilic nanoparticles, and to form a thin film nanocomposite membrane with higher permeate efficiency and low fouling potential. So, with the polymeric thin film we can embed the nanoparticles to have higher permeate efficiency and low fouling potential. The nanoparticles are designed to attract water and highly porous. So, they are designed in such a fashion. So, and soaking up water like sponge while repelling dissolved salt and other impurities. So, nanoparticles are actually they are designed in, so it will actually soak the water and repel the dissolved salt and other impurities. So, that in that way you can design. So, if we want the water to be separated from the salt and other impurities, so this type of material we can use. So, which will actually it will soak like a sponge only the water, okay, not the dissolved salt. So, in this way we can separate out the salt and other impurities from the water. The hydrophilic nanoparticles embedded in membrane also repel organic compounds. So, this type of nanoparticles we can embed with the different types of thin films or membranes to enhance the characteristics. Okay. So, it repels the organic compounds and bacteria. and the main advantage is that here in case of membranes there are pores are there, okay. And if we embed the nanoparticle hydrophilic nanoparticles within the membrane polymer, okay, what will happen? It will repel the organic compounds and bacteria, and mainly clogging of the pores take place due to this deposition of bacteria and organic compounds, and which blocks the pores. So, clogging takes place in conventional membrane, but if we use the nanoparticle nano composite material to form the membrane, in that case clogging will be reduced. So, different types of nano composites are used. The main the advantages of nano composites are that increased hydrophilicity. So, hydrophilicity will increase because of the, if we see hydrophilic component we can use. So, it will increase the hydrophilicity, it will start absorbing the water. So, water permeability will increase. So, it will reduce the pressure drop, fouling resistance will increase, and thermal and mechanical robustness. So, we can enhance the mechanical strength by incorporating the nanoparticles there, the strength will increase, even the temperature, the melting point. So, it will be thermally stable. So, we can have improve the characteristics of the membranes by using the incorporating the nanoparticles. So, to form the nano composite membrane. So, we can enhance the capability, different characteristics we can enhance, but main disadvantage is that resistant bulk material is required when using oxidizing nanomaterial. Possibly release of nanoparticles are there, possibility there to release, which may be harmful sometime. Main applications are highly dependent on the type of composite we use, the reverse osmosis we can use, removal of micro pollutants. So, different applications we can use, but that depends on the type of composites. Now, we will start discussing one different studies where we have carried out in house to develop water purification systems from nonwoven fabrics and bioactive nanomaterials. So, here also we have used nanomaterials, but also the substrate material, base material we have used the needle punch nonwoven fabrics. So, first we will try to see the objectives of the study and what are the different stages we have developed this study, divided this study, and ultimately what we have developed we have patented one water filtration system. Now, let us study. So, major objectives are, main objective is the design and development of simple sustainable water purification system, that is the main function. And why should it be simple? Because our main objective was to develop a filtration system which will be used in a rural area. Rural area people drink directly from the surface water, like pond, lakes, they try to canal, they try to drink. But to treat this water, and in village the electricity there will be problem, that type of technology will not be available. So, the simple technology should be there, where the villagers can handle or can run this purification system. That was our main objective, but we have carried out these studies in different stages. So, the sub objectives are to explore the capillary action of needle punch nonwoven fabric as a technique of water filtration. So, the capillary action of needle punched nonwovens were explored, like this is a water trough where water is there. Now, if we dip any fibrous material, say fibrous nonwoven fabric, suppose we are dipping one fibrous nonwoven, this is a nonwoven material, fibrous material, due to the capillary force, the water will draw the water against the gravity, and then this water is actually collected in another container. Here is, this is the nonwoven fabric, and water is wicked and collected in another container. So, this type of capillary action we tried to explore in the water filtration. Then what we tried to explore the nanomaterials for functionalization of nonwoven fabric for its potential water purification. We have used nanomaterials, nano silver particles we have used, and also carbon nanotube also we have silver nano rod we have produced. So, those all this we have done, we have tried to explore the different nanomaterials for functionalizing the nonwoven fabric, and then the last objective was that to design and develop a prototype zero power water purification system. So, there is no power required, using the developed needle punch nonwoven and functionalized antibacterial nonwoven cartridge. So, that we have developed. So, this study in all these stages, 3 stages, that we will discuss. First, let us discuss the wicking characteristics. So, capillary action, how capillary action helps in the water filtration. Before that, the basic motivation of our work was that our large number of people, they consume the contaminated ground or surface water. That was our basic motivation, and this happens majorly in the rural area. So, which causes the diarrhea and different types of infections we have. If you see the data, so 2.1 billion people globally lacks safe water at home. This is the data as per the 2015 UNICEF data. Okay. And 263 million people, they travel. So, they spend more than 30 minutes per round. So, 30 minutes they spend to collect the drinkable water. 844 million people, they do not have access of safe basic drinking water, and 1 59 million people drink directly from the surface water. This all these things actually with that idea we thought we should develop some cheap water filtration mechanism, particularly for rural people. With this idea, so with this idea we are, you can see here the motivations are that as per WHO that have indicate approximately 1.8 million deaths per year worldwide are mainly due to the unsafe water, and as estimated 99.8% of such death occurs in the developing countries. So, almost 100% death are in the mainly water related, unsafe water related deaths are mainly in the developing countries. So, there are different types of deaths in from 2014 to 18. So, like cholera, although it is very low, but it still exists, which is waterborne disease. Acute diarrhea disease, it is a maximum due to diarrhea, acute diarrhea, 7,000 deaths were there during these 5 years. Then typhoid death was there, and then the viral hepatitis. This is in our country, Ministry of Health data, and diarrhea you can see there are different types of symptoms are there, and different country they have the problem, like these are the different countries as per WHO. So, main challenges are there. What are the challenges? So, the actual drinkable waterless countries, if you see, they are different countries. What is the percent of people they do not get drinking water, safe drinking water? So, there are different countries. The World Bank report that more than half of the world population live in rural area and is deprived of adequate access of clean water to drink. They can't afford the advanced filtration system. So, this advanced membrane type filtration system, advanced RO filter, they cannot afford. So, like different types of advanced filtration system, electrodeionization, UV radiation, these are expensive, ion exchange, distillation. So, this type of systems they cannot afford. So, if you see, the main problem is that it is a extreme poverty and the limited electricity in the rural area, and the second problem is the high capital investment. They cannot afford, the poor people cannot afford this, and high operational and maintenance cost. Even if they purchase, the maintenance cost is very high, that also it is difficult, and absence of skillful labor. So, in rural area you will see that extreme poverty is there, electricity is not there. So, what we have to do? We have to develop one filter media which does not require any electricity. High capital investment, it should not be that complex. So, it should be simple one. So, capital investment should be low and it should be maintenance free. So, they cannot afford the maintenance, regular maintenance, it should be maintenance should be least or maintenance free, and also it's this they cannot afford any skill labor. So, they anyone can run this system and understand this system very easily. So, all these requirements were there, challenges were there. So, based on that we tried to develop our filtration system. So, the desirability was that, so we have designed and developed a simple and sustainable water purification system which has involves low level of mechanization, it should be simple one, it should have less complex, low level of complexity, very simple, and should require no electric power. So, power requirement should be 0. So, with that line what we have tried? We have tried to at different stage of filtration. So, 2 stage filtration we have developed using nonwoven fabrics. So, nonwoven fabrics were used basically to its effective filter media owing to its unique porous structure and low manufacturing cost. So, we targeted the nonwoven fabric particularly needle punched, because needle punch the nonwoven fabric is a simple one and its cost is low. So, it is a porous. So, that is a nonwoven fabrics were taken and we have used needle punched because it is more mature technology, it is available in a large volume, cheapest, allowing easy optimization. We can optimize, we can control the structure, we can control the pore structure. So, nanoscale science and engineering that we have incorporated to improve the functionalization, the solution to numerous current world problem including purification of drinking water. So, we have used nonwoven and nanoscale science in the present development. So, nanoscale science we have used, and also we have used utilization of nano bioactive and metal nanoparticles like silver less than 0.1 ppm and nanofilament wave. So, this all this technology we have used which can effectively and economically filter contaminated water. So, nano bioactive metal nanoparticles we have used and nanofilament wave we can also develop. So, in part 1 in first stage filtration what we have done, we have removed the suspended solids and turbidity. So, turbidity and suspended solids we have removed in first stage filtration, and then in part 2 of this work configuration of unique antibacterial needle punch nonwoven from silver impregnated polyester nanocomposites. So, we have developed the needle punch nonwoven using the silver impregnated polyester nanocomposite. So, polyester with nanoparticles, impregnated nanoparticles we have used to produce this needle punch fabric. So, needle punch fabric itself without this nanocomposite nano material, it removes the suspended solid and turbidity by physical means, but with the help of the nanoparticles it actually it is activated for higher antibacterial activity. Then what we have done? We have gone further. This is up to the nonwoven needle punch. After that what we have done? We have produced the electrospun nanofiber and developed on the this needle punch substrate. Needle punch this substrate we have developed. So, this is the needle punched fabric. Needle punch fabric is with the nano silver impregnated fiber, and on that we have deposited the electrospun nanofiber on this substrate, and then we have developed one prototype for 2-stage purification system. So, this is the in 4 stages we have carried out our study. Now, first stage is the removal of suspended solid and turbidity. So, for first stage filtration we can see, so this is the water trough and this water is mixed with the particles, large particles. Now, when the nonwoven needle punch, thick needle punch nonwoven is placed, this type of thick needle punch nonwoven is placed. So, due to the capillary action, the water will flow upward and it is folded, and then water will travel through this and will be collected in other. But here what happens? The particles during its movement will get trapped within the structure, and the water will flow, only water will flow, all the large particles will get trapped, turbidity will be removed. Now, we have got the polyester fiber from industry. So, 2 different types of polyester fiber we have used with shape factor 1, which is circular cross section, another is shape factor 1.3, which is tri-lobar cross section. Fiber A, fiber B, and denier remains same and cut lengths are same 42 mm. These 2 fibers were used to develop the this nonwoven fabric, needle punch nonwoven fabric, and using the needle punch DLO machine we have produced the fabric with 500 grams per square meter aerial density. And what we have done? We have changed the needle punch density and depth of needle penetration. So, using this all these parameters, we have developed different fabrics, needle punch fabric. So, fibers we have taken 2 and we have varied the needle density and also depth of needle penetration, and we have kept the aerial density 500 grams per square meter for all the fabrics. So, if you see the experimental design here, the factors which are fiber shape factor 1 and 3, 1.3, that is trilobal and circular. Needle punch density we have used 2 level 120 and 180 needle punch density, and depth of needle penetration 7 millimeter and 13 millimeter. So, design expert softwares were used. 2 power 3 factorial design is adopted here, and total 24 experimental units were there. 24 experimental units we have used here. Response is there for water filtration rate and turbidity removal efficiency. The two responses, R1 is water filtration rate, how much water flow rate, and turbidity efficiency. Then we have done the performance assessment of fabrics. So, for aerial density we have used weighing balance, thickness, SDL thickness gauge we have used, pore size measurement, we have used one instrument for pore size measurement, water flow rate, volume of water per unit time, per unit area of fabric that we have measured, and turbidity removal efficiency. In NTU we have used a laboratory turbidity meter. This is the system here. Now, here it is a contaminated water, this is the base, this here we have used the synthetic turbid water. So, standard particle we have used, not the normal soil, to make the system reproducible and reportable. So, we have used the standard turbid water, and this is the fabric specimen, and after the first stage filtration. So, we get the filtered water, and the water here from the turbid water, the water is actually wicked through the wicking action. The water is drawn and collected at this trough, and we get the filtered water. Only by mechanical the wicking mechanical action we are trying to remove the turbidity. So, the laboratory experiments were conducted using synthetic turbid water of 40 NTU prepared by adding laboratory grade clay, kaolin to deionized water according to some standard. So, that is the system we have followed. Now, after all this we have collected the water, we have measured the that filtration rate, what is the water flow rate that we have measured with the time, and also we have measured the turbidity. Okay. So, of the clean water. So, we will stop here, we will continue with these studies and also further studies. Till then, thank you.